Hello, my name is Patrick Wheeler, and I'm responsible for product management of Oracle Multitenant. In this video, I'll introduce various multi-tenant features introduced in the recent releases of Oracle Database. First, however, let's review some of the major milestones in the history of multi-tenant. Multi-tenant was born on June the 23rd, 2013. That was a very proud day, as we introduced to the family the new flagship option of Oracle Database 12c, Release 12.101. Since then it has matured rapidly, almost as if in doggy years. Release 12.2 represented grade school. That's a big step in an infant's life. And so it was for multi-tenant. We delivered some important online provisioning enhancements, along with support for software as a service use cases. With the launch of Oracle Database 18c, we had a high school graduate. Multi-tenant's backpack was crammed full of premium features such as Snapshot Carousel and refreshable PDB switchover. Multi-tenant continued to overachieve at university, graduating summa cum laude. In 19c, all database features now work in a PDB, with no exception. Multi-tenant is the foundation for autonomous database. We have completed the massive upgrade of NetSuite with 24,000 tenant PDBs. And now, with 21c, we have a responsible citizen of the world. From 21c onwards, this is the only architecture of Oracle Database. Oracle Multitenant delivers the full promise of the database cloud: isolation and agility with economies of scale. Applications run unchanged in self-contained pluggable databases, or PDBs. PDBs are simple to clone and to move to and around the cloud. A container database, or CDB, consolidates many PDBs. Patch the CDB and fix all the PDBs it contains in a single stroke. That's operational efficiency. The shared infrastructure model is highly efficient, so you can support more applications per server. That is technical efficiency. There is a fourfold value proposition of multi-tenant, and I like to check these benefits off on my fingers. 1. We minimize capital expenses, because we can consolidate more applications per server. 2. We minimize operating expenses, because we can manage many as one. Deliver standardized procedures and services, and enable self-service provisioning. 3. We maximize agility through rapid provisioning, portability through pluggability, and scalability with RAG. And 4. It's easy. Easy to adopt, because applications run unchanged. Easy to use, because SQL is the interface. So then, here's the agenda for this session. I'll start by reviewing database architectures. Next, we'll discuss various enhancements that deliver faster, easier upgrades. Provisioning has always been a strong suit of multi-tenant, and it just keeps getting better. There are several enhancements to discuss in this category. Transportable backups eliminate an obstacle to pluggable portability. Mission-critical deployments demand data guard, and the integration of multi-tenant with data guard continues to strengthen. Now, let's talk about database architectures. And the first thing to say is that multi-tenant is the architecture for the database cloud. Whether it's OCI, another public cloud, or your private cloud, this is the way to go. Multi-tenant delivers isolation and agility with economies of scale. To review a little history, the non-CDB architecture was deprecated with Release 12.2 in the summer of 2014. 19c is the last release with non-CDB, and that is the long-term support release. The prerequisite for this is that all database features must work in a PDB. In 19c, there's nothing you can do in a non-CDB that you can't do in a PDB. From Release 21c and beyond, multi-tenant is the only architecture for Oracle databases. In both releases, up to 3 PDBs may be created per CDB without requiring the multi-tenant option license. Before describing one of the key architectural innovations of multi-tenant, I want to review 2 important design goals. The first of these is portability. A pluggable database is a portable database. Relocation between CDBs is simple and fast. A relocated PDB carries with it lineage, a patch registry, encryption key information, etc. The next design goal is compatibility. Consider, for example, an application connected to an Oracle database in the old non-CDB architecture. Our compatibility design goal is expressed by what we call the PDB non-CDB compatibility guarantee, which is that you cannot tell from the viewpoint of a connected client whether you're using a PDB or a non-CDB. People laugh at me when I say this, but it's a very important principle. If we get this right, which we have, it means that an application will run unchanged in a PDB. Even if it refers to data in a remote database, it will do this by means of a database link. Upgrade all this to the multi-tenant architecture, and everything works as before, even the reference to the remote database. That makes adoption of this architecture very easy. Application changes are not required. Now I'll introduce a major architectural innovation that allows us to deliver on both of these design goals. Let's think about what happens in a traditional Oracle database over time. When we set up a so-called empty database, it's not really empty at all. By definition, a relational database includes what's known as a metadata dictionary, in which its own structure is defined. So a brand new Oracle database comes with the Oracle Data Dictionary pre-populated with the database's own structural definitions. But that's not what the database is for. You installed it to support some sort of application. I think of this great divide between the application or user data and the metadata. As you define the application and begin to use it, we begin to populate the user side of the great divide. But the metadata which defines the application, its tables, columns, indexes, functional logic, etc., are stored in the metadata dictionary, alongside the definitions of the tables, columns, indexes, and functional logic of the Oracle database itself. In the old architecture, there they were, all mixed up together. If you do a query on the data dictionary, it will typically return rows from both the Oracle-supplied metadata and the metadata for the user schema. That's been absolutely fine for all these years, but it's an obstacle to our new goal of portability. If we want to move this application from one database to another, we'd have to unpick it row by row from the origin and reinstall it at the destination. Row by row means slow by slow, to borrow a phrase from our old friend Tom Kite. To address this requirement, a major innovation of the multi-tenant architecture is what we call the horizontal partitioning of the data dictionary. We literally create a second copy of the data dictionary in what we'll call the pluggable database. Conceptually, this contains just the definition of the application. The other copy of the data dictionary lives in what we'll call the root, and at a high level, this stores just the Oracle-supplied metadata. So, how well have we delivered on our goals? It's pretty clear that we've solved the portability problem with both application data and application definition encapsulated in a self-contained PDB. We can simply move this to another route. But what about the compatibility goal? Again, it's pretty obvious that an application query, say joining emp and dept in this example, is just going to work unchanged. However, what about the experience of a DBA? In the prior architecture, a DBA would expect to perform a query against the metadata dictionary and return both data defining the application structure and definitions of objects supplied with the Oracle database itself. The problem now is that, as I've just told you, we've separated these two data sets. The solution is that we store in the PDB's data dictionary what we call stubs. These stubs are references to the full definitions of objects stored in the Oracle data dictionary. For example, there would be a stub entry in the PDB's data dictionary for our famous package DBMS-SQL. It basically says, DBMS-SQL, the full definition is down there. Now, what happens when a DBA queries against the PDB's data dictionary is effectively a union of the data definitions in the PDB's dictionary itself and, via these stubs, the definition of the Oracle supplied objects from the root data dictionary. This is how we deliver on the PDB non-CDB compatibility guarantee. From day one, Multitenant has helped speed up upgrades. This continues in 19C and 21C with some important enhancements that give upgrades an extra turbocharge. We'll talk about those here. There's a brand new upgrade infrastructure. We've further optimized the conversion of non-CDBs to PDBs, and we now automatically apply upgrades when opening a PDB in a higher version CDB. In this section, I'll describe each of these in some depth. I'll start with the new upgrade infrastructure, what we call replay upgrades. To understand the new approach, we need to go into some detail about how a traditional database upgrade works. If you're reasonably familiar with database upgrades, you'll know that this is a very flexible and resilient process. We don't deserve any sympathy, nor do we ask for any, but if you think about it, this flexibility makes this quite a challenging problem. This is why I have such a great respect for our upgrade development team. For 21C, we support upgrades in a single step from the previous version of Oracle Database, that's 19C. We also support upgrades from 18C and from 12.2. So, two basic options available to the upgrade team are as follows. Either maintain separate upgrade scripts for each supported upgrade path, what a nightmare, or maintain a single upgrade script that is applicable to all upgrade paths and is resilient enough to detect that some of the upgrade process may not apply. It is important that the upgrade does not fail when it encounters such a step. It's the second approach that we have taken. This slide shows a simplified view of this. The first two columns of the table show, for purposes of illustration, the sort of steps that might be involved in a typical upgrade. Across the top, in the grey bar, we see various upgrade paths, versions from which upgrades to 21C are supported. The last three columns show, with check marks or X's, whether each step applies to an upgrade from that version. The individual upgrade steps here are just for illustrative purposes. For example, step 1, create table DBA $something or other, was introduced in upgrades from 12.2. So that needs a check mark in the 12.2 column. However, it was already present in 18C, so upgrades from 18C and 19C do not require this step. Similarly, looking at step 5, we're dropping an index. Presumably, this was introduced in 18C. So upgrades from 12.2 do not require this step. However, it is applicable to upgrades from 18C and 19C. With this in mind, we can see that in general, any upgrade execution is going to involve some steps which are effectively no-ops, because they do not apply to that upgrade path. This is how the upgrade is written, to be very resilient. However, there is a performance cost for each of these no-ops. Individually, each no-op is pretty cheap, but cumulatively, the cost can be quite significant. In this simplistic illustration, we're only showing 10 steps. Of these, between 5 and 7 are no ops, depending on the upgrade path. That's not a big deal. Realistically though, a typical upgrade can involve thousands of steps, and the aggregate cost of all these no-ops is quite significant. The new upgrade infrastructure, introduced with Oracle Database 21c, improves performance by eliminating no-ops from the upgrade path. Here's how it works. At a high level, we utilize the capture replay mechanism introduced in 12.2 for application container upgrades. This includes a repository of the various steps involved in the upgrade of an application. This new upgrade infrastructure utilizes the same mechanism for database upgrades. As part of the database development, we run each supported upgrade path using the traditional upgrade scripts and capture in this repository all the effective steps in that upgrade path. The various no-ops are not captured. The result is a separate upgrade procedure captured in the repository for each supported upgrade path, all generated from the same familiar, resilient upgrade script that already works so very effectively. For example, referring back to the table illustrating a sample of 10 upgrade steps and the various upgrade paths to which each applies, we see that only 3 of those steps are captured for the upgrade from 18c, and 5 apply to upgrades from 19c. Incidentally, we've been using this mechanism for several years in Autonomous Database for upgrades since 18c. This new upgrade infrastructure enables fully automated upgrade during operations when a PDB is first opened after it's been moved to a higher version CDB. We introduce these new capabilities with release 21c, where we automatically run any required upgrade or conversion scripts. So just plug it in and open it up. If an upgrade is required, that will be done for you. If you're plugging in a non-CDB, it will be converted for you. I'll say more about that shortly. Technically, this automatic upgrade on open leverages the replay technology that I've just reviewed. The user simply sits back and waits briefly while a relevant upgrade or conversion is performed. The PDB will be opened read-write as soon as it's finished. Conversion of a non-CDB to a PDB is relatively straightforward and fast. But as a general rule, you can never be fast enough in computing, and we continue to invest to speed this up. Elsewhere, I have explained a fundamental component of the multi-tenant architecture that is the horizontal partitioning of the data dictionary. With that in mind, let's consider what happens when we adopt a non-CDB as a PDB. Basically, this involves plugging a non-CDB into an existing CDB root. Now, the incoming former non-CDB knows nothing about this partitioned data dictionary. It grew up in the old architecture where all that metadata was intermingled. So initially, its data dictionary includes a full copy of all the Oracle-supplied metadata. This needs to be replaced with the stubs described earlier. The script non-CDB to PDB performs this. After this is run, we have the desired horizontally partitioned data dictionary. None of this is new in 21c or 19c for that matter. What's new is the faster, easier part. In general, things run faster because we've eliminated unnecessary invalidation of customer-defined objects. We needed to focus on conversion of Oracle objects. Customer objects need not be impacted. This means that the conversion timing is going to be more consistent, regardless of the number of objects in the non-CDB. Furthermore, the effective steps in non-CDB to PDB.SQL are now captured in the new upgrade infrastructure. This means that the conversion can now happen automatically on PDB open, as with other upgrades. Provisioning has always been a strong suit of multi-tenant, and it keeps getting better. There's a lot to discuss in this category. First, I want to be sure you understand what's happening behind the scenes during a hot clone. This is an important background for the various enhancements that we have in the next few sections. Faster, easier encryption and decryption operations, snapshot clones on ACFS, precision cloning on Snapshot Carousel. So let's explore the inner workings of cloning. First, we need to explain what's involved in a cold clone from a technical perspective. A cold clone is a relatively simple operation to understand. The source PDB must be in a quiescent state, hence the term cold clone. Basically, you close it and reopen it in read-only mode. In this state, there are no incomplete transactions and all blocks are flushed to disk. Performing a cold clone is therefore simply a matter of scanning all the blocks of the source and copying them to the destination. Even this is a sophisticated operation, however, as parallel slaves will automatically be invoked to optimize performance. Once the clone is complete, the sourced PDB can be reopened read-write for processing to resume. So we can do cold clones. Why not just do hot clones? It's easier said than done. I shall explain why. Before we get into that, let me illustrate what is going on in a database which is open read-write. Here we use color coding to show the passage of time, as illustrated by the clock in the upper left corner. So in the first time interval, we could think of this as yellow time. We see some data changes in blocks scattered throughout the data files on disk. Corresponding to this, we have undo segments in the undo table space, and of course redo segments written to the redo log file. Each of these changes is color-coded according to its time interval, in this case yellow. Notice that some of these changes, data file blocks, undo and redo, have check marks. These indicate that the change is associated with a committed transaction. Now, as we move into brown time, we see more changes. Notice that one of these changes is to commit a transaction that began in yellow time. All of this is summarized in the legend on the right side of the slide. We can now watch the database activity proceed as we progress through slate, steel, and charcoal time. The point of all this is that in general, we must assume that this sort of activity is going on in a database which is open read-write. That is, transactions are changing data blocks scattered throughout the data files, and it is not reasonable to assume that at any time there are no uncommitted transactions. Hot cloning needs to take account of all of this activity. With all these changes going on, it is hard enough to guarantee that the clone be physically consistent with the source. However, what is required is that it be transactionally consistent with the source as well. Incidentally, this is why it's very important not to rely on storage-level replication technologies alone to clone your databases. If you do so, the operation will appear to complete successfully. However, there are likely to be some transactional inconsistencies. Now that we understand the challenges to be addressed by an online, that is a hot clone, let's see how it works. Again, we'll use color coding to illustrate the passage of time. We begin the online clone operation in yellow time. As with the cold clone, we do a parallel scan of the data files. In this illustration, during yellow time, we can scan the first two rows of blocks as shown. These are read and copied over to the target. So far, everything is okay. All changes made to blocks in the source that we've scanned so far are copied over to the target. Now, as we run into brown time, we scan the next set of blocks. Again, there are some changes made in brown time that are picked up by this scan and copied over to the target. However, there are also some changes made to blocks which were previously scanned. These changes are therefore not reflected in the target. And now we can proceed through the slate, steel, and charcoal time intervals. As before, we see that some of the changes made in the primary during the cloning operation are reflected in the target. However, some changes made to the primary during the cloning operation happened after those blocks were scanned. Those changes are not yet reflected in the target. Here we see, with the red X's, the blocks in the target in which the corresponding block in the primary has been changed, but that change is not reflected in the target. So far then, we have copied all the blocks from the primary to the target, but because the primary was changing while the blocks were being scanned, what we might refer to as a fuzzy read, the target is not physically consistent with the primary. The next step is to fix that. This is done by copying over all the redo that has accumulated since the cloning operation began, scanning it, and applying all those changes on the target. The result of that is a physically consistent clone on the target. However, note that not all the transactions in this physically consistent clone are committed. It is now necessary to roll back any uncommitted transactions. This is done by applying the undo corresponding to those uncommitted transactions. When this is complete, the clone is in a transactionally consistent state. The relevance of all of this from a high availability perspective, of course, is that hot clones allow cloning operations to be performed whenever necessary without incurring an outage in the source system. Now we move on to the topic of encryption of PDBs. In general, no single technology is sufficient to provide comprehensive security. Oracle's philosophy is defense in depth. What is required is a suite of complementary security technologies to protect against a broad range of threats. Prominent among these is transparent data encryption, or TDE. With multi-tenant, each PDB can have its own encryption key. A typical requirement is to encrypt an unencrypted PDB as it is migrated to the cloud. Remember that there are many options in Oracle Cloud, but security is not one of them. PDBs must be encrypted in OCI. For this reason, rekey is the default mode. However, on rare occasions, in non-OCI deployments, the DBA may choose not to encrypt the PDB. If no encryption is required, say no key. From a security perspective, it's good practice to rekey PDBs periodically. However, historically, this could involve downtime, which of course may impact operational availability. With this new capability, these operations are now possible with near zero downtime. Next topic, snapshot cloning. We'll start with a review of some of the basic concepts in storage-efficient clones. Consider first a basic file copy operation. A file is a collection of data blocks and headers. A basic copy operation duplicates both the data blocks and the file headers. It's effective and simple, but it's expensive too. In many situations, the two file copies are only expected to differ slightly. In these cases, it's inefficient to create these full copy clones. Where two files are expected to be substantially similar, copy-on-write technologies can be far more efficient. This approach is illustrated here. Again, the file is a collection of blocks and headers. To create what is apparently a full dataset copy of the file, all that's required is to copy the header. This copy, typically implemented with a sparse file, points to exactly the same data blocks. It's only when a change is made to one of the files that the affected block or blocks are copied and changed. The file header for the changed file continues to point to the unchanged blocks it has in common with the source file. However, references to the affected blocks are updated to point to the changed block copies. This is why the technique is known as copy-on-write. This is the fundamental technology that underpins snapshot cloning in multi-tenant. However, various storage technologies differ in subtle ways that have important implications for how snapshot cloning behaves. A seemingly subtle, but nonetheless critical difference is whether the snapshot is taken at the file system level or at the file level. First, we consider file system-based snapshots with a single file system for the entire CDB. Here we'll walk through some typical lifecycle operations. As I do so, pay attention to the column on the right that shows the aggregate storage consumed by PDBs in this CDB. We start by creating the first PDB red. Let's assume that it consumes 10 gigabytes, so the total storage for PDBs is now 10 gigabytes. Next, we create PDB green and PDB gold, each consuming 10 gigabytes, so our total storage at this stage is of course 30 gigabytes. Next, we'll drop PDB green. Guess what? The storage goes down to 20 gigabytes. It all seems very obvious. But now, things get interesting. Pay attention. Now, I'll create a snapshot copy of PDB red. Because this is a storage-efficient clone, it will require negligible additional storage, although it's apparently a full dataset copy of PDB red. Under the covers, we're using the copy-on-write technology, and therefore the overall PDB storage is essentially unchanged at 20 gigabytes. This is outstanding. What appears to be a full dataset copy consumes negligible incremental storage. Therefore, very little I/O is required, and the operation completes very quickly, even for a substantial PDB. At the bottom on the left, we can see the file system level snapshot that supports this clone. So far, so good. But now we'll see how things can go wrong. Watch carefully. Now I'm going to drop PDB gold. But notice that the storage remains at 20 gigabytes. What's going on here? I've dropped PDB gold, and I expect that its storage, 10 gigabytes, would be released as a result. But because of the file system snapshot that enabled the snapshot clone of an apparently unrelated PDB, red, that storage is held hostage and cannot be released. It turns out then that these apparently unrelated PDBs have a dependency in the file system. You can imagine how it might be possible to actually consume more storage, not less, when using snapshot cloning than with regular cloning, if there is a lot of creation and dropping of PDBs going on in an environment where snapshot cloning is also taking place. Clearly, this is an undesirable outcome, and the workaround is to have different file systems within the CDB. Let's move on to consider the same example when snapshots are taken at the individual file level. This is how Oracle ASM Cluster File System, or ACFS, works. We start by creating our three 10 gigabyte PDBs, red, green and gold. As expected, our total PDB storage is now 30 gigabytes. Again, there are no surprises when we drop PDB green. Its 10 gigabytes are released, and now we're down to 20 gigabytes. ACFS supports snapshot cloning, of course, and so when we create the snapshot clone for red, there is insignificant growth in storage. Looking into the storage layer, we now see only the sparse files associated with PDB red. That's all that's required to implement the snapshot clone. This is a file-level snapshot. Importantly, because it doesn't involve the data files for any other PDB, when we drop PDB gold, we see the storage drop down to 10 gigabytes as expected. So it may seem to be an arcane difference, but you can now appreciate how consequential it can be. The next slide summarizes this and other important capabilities across various storage technologies. For each type of storage listed, we see how snapshots are enabled, whether clone sources are read-writable or must remain read-only, whether snapshots are taken at the file level or the file system level, as we've just discussed, and whether split mirror cloning is possible. Without reading the whole slide out for you, we can see that ACFS has ideal characteristics. It supports snapshot clones natively, the clone source remains read-writable, which is important for Snapshot Carousel, and that snapshots are taken at the file level, so storage is not held hostage when dropping apparently independent PDBs. Now, we can move on to discuss the Snapshot Carousel. This is a repository for periodic, point-in-time copies of a PDB. For example, we might take nightly snapshots of a particular PDB. It makes sense to limit the number of historical snapshots we take. Perhaps we only need snapshots for the past week. The maximum number of snapshots to be retained is configurable. The default is 8, which is also the highest value that is currently supported. Every 24 hours, at midnight, we drop the oldest snapshot. You can think in terms of the carousel rotating by one slot. The newly vacated slot becomes the slot for T0. A fresh snapshot is taken, and this is dropped into slot T0. The process repeats the following midnight, as the calendar flips from Tuesday to Wednesday. And again from Wednesday to Thursday. And Thursday to Friday. The snapshot carousel can be very helpful for debugging date-specific problems. For example, we might have a problem reported on Friday. It's a new problem, which seems to be data-related, and arose earlier in the week. However, the report is not specific about the exact date on which it was first encountered. We might try a bracketing approach. Take clones from the snapshots from Monday, Tuesday, and Wednesday, and run tests to see whether the problem shows up. The problem was not reproducible on Monday, so we can eliminate that date. Further testing shows that the problem shows up already on Tuesday. Therefore, we can eliminate Wednesday too. We now drill into Tuesday in more depth. You'll notice how agile this process can be. These are the sorts of capabilities that modern, cloud-based development organizations require, so that they can keep up with the demands of the modern business climate. Technically, snapshots can be materialized either as full clones or as snapshot or thin provision clones. Another great use case for Snapshot Carousel is as a convenient source for simple point-in-time recovery of a PDB. Let's say a few days go by uneventfully. Business proceeds smoothly, and snapshots are taken automatically every midnight. But then, on Wednesday the 28th, we discover that a serious data error was introduced the previous day, Tuesday. It is determined that the simplest remedy is to recover from Monday's snapshot taken before the data error was introduced. We simply drop the current PDB and restore a clone of Monday's snapshot before the data error was made. An important enhancement to Snapshot Carousel, delivered with Release 21C, is precision cloning, as of a specific timestamp or SCN. In this illustration, snapshots are taken daily at 2 a.m. Our intention is to recover to 7:26 and 41 seconds on Tuesday, October the 5th, 2021. Here's the syntax. Create PDB red from gold using snapshot Tuesday at timestamp. Nice and easy. Let's see what happens behind the scenes. We clone the specified snapshot, in this case the one from 2 a.m. that morning, and then roll forward to the required timestamp using the archive logs. Using very similar syntax, it is also possible to specify the recovery point in terms of an SCN instead of a timestamp. Let's turn our attention now to another important enhancement: transportable backups. A sound backup strategy is, of course, a fundamental element of any high availability system. A very basic backup strategy is to take periodic full backups. Perhaps you'd do this every Sunday at 2 a.m. At least you've got a backup, but it's a pretty primitive strategy. In the event of a failure, the recovery point, RPO, would therefore be the previous Sunday at 2 a.m. Weekly full backups, combined with retained archive logs, enable point-in-time recovery to any time during the week. That's a far better RPO than is achieved with the weekly full backups alone. However, recovery through several days' worth of archive logs can be quite a lengthy procedure. Therefore, the recovery time, RTO, is in general relatively poor with this strategy. So with good RPO but poor RTO, we might pronounce this strategy as tolerable. An established best practice with RMAN-based database backups is shown here. We have periodic full backups with regular, incremental backups taken at intervals in between. A typical model is to take weekly full backups, perhaps Sunday at 2 a.m., and then daily incrementals, perhaps taken at 2 a.m. on every other day of the week. Archive logging is also enabled. This is indeed a very respectable strategy. It delivers good RPO, since pitter to any point in time is possible, and it delivers good RTO, since restoring from a full backup, then applying the required incrementals, and then recovering from the archive logs to the required point in time is a very efficient strategy. This slide illustrates a point-in-time recovery. In this example, we're using a typical backup strategy involving weekly full backups and daily incrementals. Let's say that at lunchtime on Thursday, we decide to recover to 10 a.m. on Tuesday. That's what you tell RMAN to do. What RMAN does behind the scenes is to restore previous Sunday's full backup, apply incrementals from Monday and Tuesday, and use archive logs to recover from Tuesday at 2 a.m. until Tuesday at 10 a.m. So far, so good. But what happens if the PDB I'm recovering had been moved between CDBs since Sunday's full backup? For example, this might have happened at noon on Monday. Here I provide a little historical context. This is more relevant for those with experience of prior releases of multitenant, but may also be of interest even if you're looking at multitenant for the first time. In prior releases, to achieve the same point-in-time recovery, at lunchtime on Thursday we decide that we want to recover until 10 a.m. on Tuesday, the pitter was still possible, but more complicated. You would restore to an auxiliary instance, recover to the point before unplug, manually move the data files to the new CDB, roll forward to the desired point in time. In practice, this additional complexity could limit the agility of moving PDBs between CDBs in previous releases of Oracle Database. The transportable backup feature, now available, eliminates all the additional complexities associated with a pitter in a situation where the PDB in question had been moved between CDBs since the last full backup. The point is that, with transportable backups, you can perform a PDB pitter to a time after a PDB has been moved, but before the next full backup. This works whether the PDB has been moved via unplug-plug or online PDB relocation. In this section, we'll discuss considerations for provisioning PDBs in high availability configurations, protected by DataGuard. Two familiar technologies cover both extremes in terms of data replication. At one extreme, DataGuard, or preferably active DataGuard, can be configured at the CDB level. This is a great example of managing many as one. and thus reducing operating costs. Configure this once at the CDB level, and DataGuard will replicate transactions from primary to standby for all PDBs in a single stream. Some granular control is possible to the extent that a PDB may be configured with no standby, where appropriate. At the other extreme, for replication of data at the individual PDB level, Golden Gate is the perfect choice. With Golden Gate, it is possible to have bidirectional replication between CDBs, as is shown here. This can even be used in an active-active configuration, which is a key capability for supporting a truly zero downtime upgrade. Important considerations apply to certain forms of PDB creation in DataGuard configurations. Two of the most common provisioning operations, creating a new PDB from seed and creating a local cold clone, work absolutely fine with DataGuard. Let's walk through an illustration of this to understand what's going on. Here we see a high availability configuration with a primary CDB at the top and a standby CDB at the bottom, with replication managed by DataGuard. We begin with a new CDB with no customer-created PDBs. Only PDB seed is present in this initial state. When we create a new PDB from seed, the create PDB operation replays successfully on the standby. This is possible because PDB seed, including its data files, is already present on the standby. The new PDB is created successfully on both the primary and the standby. Similarly, a local cold clone, that is, a clone of a PDB already present in the primary and open read-only, will succeed and replay successfully on the standby because it is already present in the standby, including all the data files necessary to process the operation. However, for various reasons, some other provisioning operations are more complicated. For example, a hot clone, that is a clone of a PDB performed while the source PDB remains online, in other words open read-write, is complicated by the fact that there are two recovery operations involved at the same time. One is to ensure that the hot clone itself is transactionally consistent, as we saw in a previous section of this presentation. The other is the application of redo on the standby performed by DataGuard itself. These two recovery operations would interfere with each other, and to avoid that, a hot clone to a DataGuard primary will have no standby replica. This may be viewed as the functional equivalent to including the clause standbys equals none in the hot cloning operation on the primary. For the purposes of this discussion, a remote cold clone, that is, a cold clone of a PDB in another CDB, is comparable to a plug-in of an unplugged PDB. In both cases, unlike creating a new PDB from seed or performing a local cold clone, by definition, the data files for the newly created PDB are not already in the CDB. Therefore, the complication in these cases is that not only do we need to copy the data files for the new PDB into the primary CDB, we also need to copy them onto the remote CDB. With these considerations in mind, we introduce some special procedures to ensure smooth provisioning of PDBs in DataGuard configurations. These involve some additional one-time steps in the process of setting up the DataGuard environment, and a simple procedure to follow in each of these somewhat more complicated provisioning cases. Let's discuss the additional one-time steps involved in DataGuard setup. We start by creating a self-referencing database link on the primary. This replays successfully on the standby to create a database link referencing the primary. Next, we set a parameter on the standby. This is named standby PDB source file DB link, and it should reference the database link created in the previous step. Finally, CDB root of the standby should be opened read-only. Note that no active DataGuard license is required if only CDB root is opened read-only on the standby. This allows DataGuard to read the value of the parameter just specified. When a create PDB operation is replayed on the standby, but the required data files are not already present on the standby, these data files may be copied from the primary via this DB link. Now we introduce a simple new procedure employing what we refer to as a transient no standby PDB. Following this procedure ensures that even these relatively complex provisioning operations can be achieved in a few trivial steps. For example, let's say that our intention is to plug in an unplugged PDB or to perform a remote clone. We want this new PDB to be named PDB3. We start by creating what is referred to as a transient no standby PDB. To do this, simply include the clause standbys equals none in the create pluggable database statement. The result of this is that on the standby, the transient PDB will be visible in mounted state, but its data files will show as offline. Next, we create the desired PDB, PDB3, as a local cold clone of the transient no standbys PDB. This replays successfully on the standby by copying the PDB's data files across the database link identified by the parameter standby PDB source file DB link. The transient no standby PDB may now be dropped. So what seemed to be a relatively complicated procedure is reduced to this simple 1, 2, 3. Follow this same simple 1, 2, 3 procedure for hot clones in high availability configurations protected by DataGuard. As before, the first step is to create the transient no standby PDB, this time as a hot clone. Again, it's important to include the clause standbys equals none in the create pluggable database statement. Remember, the intention of a hot clone is to take the clone while the source remains online. Of course, this is consistent with our high availability theme. And clearly this requirement is met in this case. Next, we create the desired PDB, PDB4, as a local cold clone of the transient no standbys PDB. This replays successfully on the standby by copying the PDB's data files across the database link identified by the parameter standby PDB source file DB link. The transient no standby PDB may now be dropped. As you see, we can use this same simple procedure employing the transient no standby PDB technique for provisioning operations in environments protected with DataGuard. Recovery Isolation Mode is an enhancement to DataGuard introduced with 21C. I'll show you how it works. Here we have an active DataGuard configuration with a primary CDB on top and the standby CDB on the bottom. We see the so-called media recovery process, or MRP, replicating transactions from primary to standby. When we provision a new PDB, red, in the primary as a hot clone of green, an isolated media recovery process is spawned. This ensures that the MRP associated with instantiating the new PDB and its corresponding standby does not interfere with the main MRP. Once the new PDB and its standby are fully instantiated, the main MRP can take over. Wow, we've covered a lot of ground in a single session. We briefly reviewed database architectures, our design goals, and some fundamental enabling innovations. Next, we covered 3 important enhancements that deliver faster, easier upgrades. Provisioning just keeps getting better. There are several enhancements to discuss in this category. Transportable backups eliminate an obstacle to pluggable portability. Mission-critical deployments demand DataGuard, and the integration of multi-tenant with DataGuard continues to strengthen. Thank you for your attention in this session. I hope that you enjoy the rest of what Oracle Database World has to offer.